Namaskar and hello. Welcome to your favorite Shridevi classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our playlist class 12th physics and physics made easy, we'll discuss some more multiple choice questions on electrostatics. Let's start. We start with a very common and very important examination question pattern. Given is the force on 2 coulomb charge at a distance 4 meter from a point source charge capital Q is F. In the electric field of same point charge, we have to find out potential at a distance 2 meter from source charge. So from amount of force, we can find out electric field intensity at test position 4 meter distance from source charge as force per unit test charge, and 2 coulomb has force F, then 1 coulomb would have force F by 2, and that become electric field intensity at 4 meter distance. In electric field of point source charge, potential is KQ by R and electric field intensity is KQ by R square, and potential and electric field intensity at the same point are related with each other as given by this yellow highlight relation. And from electric field intensity we can find out potential at same test position, which is 4 meter from source charge, and when R is put as 4 meter, potential at 4 meter comes as 2F in volt unit. Now potential is inverse of the distance of test position from source charge. So at 2 meter distance, which is half of 4 meter, potential become 2 times. So at 4 meter potential is 2F. So at 2 meter potential will become 4F in volt unit. So option 3 is right choice. It is given that in an uniform electric field, force is F on charge Q. What will be the work done in moving a test charge capital Q by a distance D along electric field direction? In uniform electric field, everywhere the strength of electric field is the same and it is force per unit charge. So it is F by Q in our case. Now in this uniform electric field, when we put a test charge capital Q, then force on that capital Q charge would be E into Q, or F by small q multiplied by capital Q. And when displacement is made along the direction of force, work done is product of force multiplied by displacement. And for D displacement of test charge capital Q in the same uniform electric field would become FD capital Q divided by small q. Here F by small q is strength of electric field, and strength of electric field multiplied by capital Q would become force on capital Q, and force when multiplied by displacement will give us amount of work. So option 3 is the right choice. In this question we have to find out change in potential when a negative test charge is moved opposite to the direction of electric force lines from B to A, whereas electric force lines is directed from A to B. So we know electric force lines are directed from high potential to low potential. So point A is at high potential and B at low potential, and irrespective of test charge polarity, if we move against electric field, it's a positive change in potential. So here when we move from B to A, the potential will increase. Option 2 is the right choice. Now in this positive potential difference, the movement of negative Q charge will not require any work from external agency, and work done on electric field is called negative work, as this charge will move by itself by the force of electric field in opposite direction of electric force lines. So B to A movement of minus Q charge involve a positive change in potential difference and negative amount of work done. 4 charges of equal Q magnitude are placed on a line at 0 meter position, 2 meter position, 6 meter position and 10 meter position. We have to find out the resultant force on this Q charge placed at 6 meter position. So this charge will have force from these 3 charges, and as per superposition principle, total force on this charge is vector sum of force contribution by individual charges. And here 2 charge position of 2 meter and 10 meter are having 4 meter separation from 6 meter position, and identical polarity charge have mutual repulsion. So this charge at 2 meter position will produce electric repulsion of K Q square upon 16 Newton along this arrow direction, and this charge of 10 meter position will produce same amount of repulsion force in just opposite direction, and vector sum of these two electric force of 2 meter position and 10 meter position charges being equal and opposite will become 0, and resultant force would become force contributed by this charge of 0 meter position having 6 meter meter distance, and force is K Q1 Q2 divided by distance square, or K Q square by 36. So here first option is the right option. In the similar condition, if one has to find out force on this Q charge placed at 2 meter position, then we will found that force of this 0 meter position at 2 meter distance will produce a repulsive force of KQ square upon 4, where 4 is distance square. Distance is 2 meter and 2 square is 4. Similarly, charge of 6 meter position and 10 meter position will produce respectively KQ square by 16 and KQ square by 64 force of repulsion in opposite direction, and resultant force would be difference of bigger magnitude minus smaller sum magnitude of these two. And if we calculate, we'll found that resultant force on this Q charge would become 11 by 64 KQ square in this arrow direction, as electric repulsion of this Q charge is greater than sum of forces of 4 meter distance position and 8 meter distance position. Charges on 5 vertices of regular polygon R and minus Q. The center got a distance small r from any vertex. We have to find out resultant electric field intensity at this center of regular pentagon. Now pentagon is not a symmetrical charge distribution as square or hexagon may be. So from superposition principle, resultant electric field of 5 charges as vector sum of all individual contribution become quite difficult to analyze. But if except one vertices, all other vertices got identical charge, then things become quite simple to make such calculation. Here this different charge can be converted as a charge which is identical to charge of other vertices, and a remaining charge minus Q become equivalent to sum of minus 2Q and plus 1Q. These two are just identical. Now if a regular polygon got identical charge at all vertices, then resultant electric field contribution of these green highlighted 5 charges at this origin becomes 0. So this minus 2Q charge will produce an electric field K2Q over R square in this blue arrow direction, and that become resultant electric field of Q, 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 Q and minus Q. So this option second is our right choice. Now such questions can only be solved when only one vertices got different amount of charge and all remaining vertices got identical amount of charge. Uniform electric field of strength Ex exists in X direction. What is amount of work done in moving a positive plus Q charge from coordinate 0, 3 of position A to position B having coordinate 4, 0? This total displacement is of course 5 meter, but in uniform electric field the work done calculations are done by moving charge from same initial to final position by an alternate path which is either perpendicular to electric field lines or is along electric field lines. In electrostatics, amount of work done between two positions doesn't depend upon path followed, as electrostatic field is conservative field. So amount of work done from A to B is equal to amount of work done in alternate path shown by this blue arrow position, and when we move from A to O normal to electric field direction, our displacement is perpendicular to direction of force, so there won't be any work done from A to O. And from O to B, this positive charge will experience force in the direction of electric field, and displacement in the direction of force will result in work done, and this displacement is 4 units. So amount of work done is force multiplied by displacement. Since work is done by electric field, not by external agency, so such work is called negative work done. In fact, position A is at high potential position with respect to position B, and potential difference between these two positions is 4Ex, and when a positive charge moves from high potential to low potential, the work done is negative on electric field by external agency. So option second is a right choice here, though the displacement is 5 meter, but displacement in the direction of electric force is only 4 meter. In the similar displacement of positive Q charge from A to B, if electric field is directed in plus Y direction, then for this 5 meter displacement we can find out work done by path along direction of electric field and normal to electric field, and in 0 to B 4 meter displacement is normal to the direction of electric force, so this 4 meter displacement won't involve any amount of work done, and work is required only in A to O position movement. Positive charge would have force in the direction of electric field as shown by this blue arrow, and against this force when we make this 3 meter displacement, we have to do positive 3q ex work. So this plus 3q ex would, so positive, so q ey is force on positive charge, and against force 3 meter displacement will involve positive work done of plus 3q ey joule. This is a very good and important conceptual objective question. 2 point charges as source plus q and minus q are given, and there are two test position A and B having distance d, and A got a distance A from positive q charge and B got a distance again A from negative q charge, and we have to find out potential difference between A and B, that is VB minus VA. So for this example, we have to first apply superposition principle and find out potential at position B and A by addition of potential contribution of individual charges. So at each test position A and B, positive q charge contribute positive potential and negative q charge contribute negative potential, and the sum of two, one positive quantity and second negative quantity, numerically subtracted give us resultant potential, and difference of potential of B and A position will become our potential difference. At position A, this positive q charge at a distance A from it produce positive kq upon A potential. Similarly, this negative q charge having distance A plus D produce a negative potential, and when we take LCM and simplify things, A will get cancelled out, and positive potential of position A comes as kqd divided by A multiplied by A plus D, and this charge distribution got asymmetry, where at position B this negative q charge will produce negative potential of this amount and this positive charge will produce positive potential of this amount. So at B position, potential is again kqd divided by A multiplied by A plus D, but with negative sign. So B got negative potential, A got positive potential, and the magnitude of potential is kqd upon D multiplied by sum of A plus D, and the difference of B potential and A potential is twice and negative. If this question has asked VA minus VB, then this potential difference will become plus 2 kqd upon D multiplied by A plus D. On the x-axis at 2 meter, 4 meter, 8 meter, 16 meter positions, we have given identical q charge positioned, and this charge distribution with doubling distance extended up to infinity. We have to find out a resultant electric potential of all the charges at origin. So as per superposition principle, total resultant potential at origin is potential contribution of all individual charges. So charge at 2 meter position will produce electric potential kq divided by distance 2 meter, and in place of k I can write 1 upon 4 pi epsilon. Similarly, for 4 meter distance electric potential, 8 meter distance and 16 meter and so on, I can find out individual potentials, and sum of all those potential is a resultant potential contribution by all charges distributed up to infinity. Now this is a geometric progression of common ratio less than 1. So this infinite GP got a finite sum, and the sum is given as first number A divided by 1 minus common ratio, and common ratio here is half, and A 1 minus R when simplify comes as 1. So this sum in blue frame is 1. So electric potential of all charges acting together at origin will become Q upon 4 pi epsilon. So this second choice become the right option here in this question. In the same example, if alternate charge got opposite polarity with doubling distance up to infinity, the electric potential at origin by first positive charge is positive and second negative charge at 4 meter distance is negative. So one quantity is positive, one potential quantity is negative. Again, this is an infinite geometric progression with common ratio negative 1 by 2, and sum of blue frame series is 1 upon 3, and resultant potential at origin by this charge distribution become Q upon 12 pi epsilon. In the same charge distribution of previous example, alternate positive Q and negative Q charge are placed at x-axis on 2 meter, 4 meter, 8 meter, 16 meter, 32 meter, and with doubling distance up to infinity. And now we have to find out resultant electric field at origin by all these charges distributed up to infinity. So electric field intensity is a vector vector quantity and charge placed at smaller distance position. Positive Q charge at 2 meter distance will produce outward electric field of kq by distance square, kq by 4 in this blue arrow. Similarly, all positive charge of 8 meter position will produce 8 square 64 kq over 64 electric field, and so on. Whereas all these negative charge will produce inward electric field of kq over r square value. So this 4 meter charge will produce kq over 16. Now since electric field of negative charge is opposite to electric field of positive charge, for vector summation we have to subtract. So resultant electric field in this direction will become this summation, and again this is a geometric progression with first number 1 by 4 and common ratio minus 1 by 4, and sum of infinite geometric series in yellow highlight is a1 minus r, and this summation is 1 by 5. So resultant electric field at origin by all these charges up to infinity is kq by 5 volt per meter. In the similar example, if all charge got identical positive polarity, then all will produce electric field in the same direction. Of course, due to different distances, this 2 meter got 2 square kq by 4 volt per meter electric field intensity. 4 meter distance position charge will produce kq by 16. 8 meter will produce kq by 64, and so on. Again, this is a geometric progression with first number 1 by 4 and common ratio again 1 by 4, and simplification results in 1 by 3. So resultant electric field intensity of all those charges distributed up to infinity is kq by 3 volt per meter at origin. In electrostatics, we come across several physical quantities and we have to find out which one is scalar quantity. So given is potential gradient. So potential related to work done per unit charge, work is a scalar quantity. So potential is also a scalar quantity, but potential gradient is maximum rate of change of potential with displacement, and it got a direction just opposite to direction of electric field intensity. So potential gradient is a vector quantity, whereas potential itself is a scalar quantity. Similarly, electric flux is a dot product of field intensity and area vector, and dot products are always scalar quantity. So electric flux is scalar quantity, and positive enclosed charge contribute positive outward flux, and negative enclosed charge produce negative inward flux. So flux is a scalar quantity, but flux density equivalent to electric field intensity is not a scalar quantity. So here potential gradient is a vector quantity and electric flux is a scalar quantity. So it's only option 2 which is scalar. We have discussed 10 different type of question patterns which are very important from examination point of view in this Physics Made JEE MCQ series. Our other video in the same series will definitely help you to achieve high score in all type of competitive exams. We once again appreciate your interest and support in viewing and promoting our videos. Thank you very much.